All right, so the next part we're going to zoom in and we're going to look at the finishing off the graph coloring algorithm. So I mentioned that we're going to do this optimistic coloring algorithm. This is the typical algorithm that you'll find in a textbook. There's variations on this algorithm that add additional complexity, in particular dealing with variables that actually should be allocated to the same register. But we're not going to go into that detail. That is something that I think you will need to deal with in a real compiler. But for the just approximation that we're doing here, it should be enough to just look at this algorithm here. So we start off with a number of registers that the machine supports. That's usually we got to give it a letter. We call it K. So we'll assume that we're compiling this interference graph that we've gotten from some program by doing liveness analysis. And our machine has 3 registers. The way the optimistic coloring algorithm works is we're going to use a stack. That's what it's called, stack-based. And each step, we're going to take the graph and we're going to pick a node. And we're going to try to pick a node if such a node exists so that its degree is less than k. And of course, the degree means the number of edges that it has to other nodes. Okay, and we're going to pick that node and we're going to remove it from the graph. So let's say we pick V1. So it has to have less than k neighbors, and we put it in the stack. And if we remove it from the graph, we're basically going to remove both the node and the edges, which means that its neighbors are going to be reduced in degree. So if we remove V1 from this graph, then we can see both V3 and V4, and V2 will not be less than 3, so we can't pick it. So we see we get new candidates. So let's say we pick V3, we put it on the stack. So we're going to just keep doing that. Search for my bad handwriting. So V1 and V3 are now on the stack. Those are out of the graph. So now actually V2, V5, and V4, actually all of them are going to be less than k. So it doesn't actually matter. It turns out that in this graph, we could pick almost any order except starting with V2. So if we do that, then we end up with something that looks like this. So these are all now nodes that are on a stack. And then we just start popping the stack. And we give a node a color. So when that terminates, so each node is going to get a color when it gets popped off the stack. Okay, so if we go and pop V2 first, we've got to pick a color. So thankfully, I've got 3 colors, so we're going to go with red for V2. And then when we pop V5, we have to make sure that we don't assign it a color that is the same as any of the neighbors. So it needs to be either blue or green. So let's say we do blue. Okay, so then after we pop V5, we pop V4, and again, we have to pick a color that doesn't interfere, that's not the same as any of its neighbors. So it turns out we can also use blue for that one. Then we've got to pop V3. So this one has to be, it cannot be red and it cannot be blue, so it must be green. And then we're down to our last one, which is V1. So that one cannot be red or green, so it must be blue. All right, so the key insight is this step here. When we pick a node of degree less than k and we put it on the stack, that means that when we're unwinding the stack, there will be a color for that node. So this is what the simple greedy heuristic gives us, is that we don't assign it a color right now, but we know that when we do assign it a color in the future, there will be a color because its degree is less than k. Okay. So where does this break down is if you get to a step here where you're trying to find a node of degree k, or less than k, and you can't find one. So what happens then? And this is where we do spilling candidates. So you might be tempted to think that we spill a node, meaning that we're going to allocate it to memory and it's not going to get a register right away. But it turns out that if there is a node in the graph, so that if there is not one, sorry, less than k, that means that they're all k or greater. We pick one. And we remove it from the graph. We could think of putting it onto the coloring stack and just marking it. So for example, let's just suppose that when we popped V2, or sorry, V5 or one of these, we just marked it as having a lot of edges, neighbors. But the idea is that since we're assigning colors when we pop the stack, what that really does is it just means that the graph got simpler to color. Okay, so in that case, we're effectively being optimistic. That's where this optimistic coloring comes in, is that basically we're assuming, oh, well, we don't have a color right now. We know that this is a problem case because this node has a lot of neighbors, but it just may be that when we get down to it, popping things back, there will be a color available. Okay, so that goes on to the, as a candidate. It turns out that often, even though we run into the situation where there's some node and we can't make progress that we have to remove, we can end up coloring it anyway. And unfortunately, there's no way to know that for sure because graph coloring is NP hard, so any of these things are really not exact things, they're approximations. Okay. So real spills are decided at coloring time. Okay. So what does a spill actually mean? A spill means that a variable cannot get a register. So when we get to putting it back into the graph during this popping part, there are no colors available because everything around it has already got a color. And so it is going into memory. So wherever that variable is used, let's say that we did VS as a spill, if we use that in an expression, then we must load it from the stack before that expression. And similarly, if we compute it, define it, we store it right afterwards. And store is like a, store to the stack. So this is called spill code. This has to be inserted into the program to load and store these things from the stack frame. And we just assume that the stack frame can get as big as we want, so we'll always be able to spill things into memory on the stack. Okay, so that means that it actually changes the program, and actually, this load has to load into something that we're going to use. So this is actually like a new variable. It's a new variable with a very small lifetime, right? It's defined by this load, and then it's used once right before the original use in the original program. Same here. This is the original variable, and we've basically cut it off. So that means that previously VS was live, right? It got defined somewhere above, and we've basically just chopped that off, and we've made a little tiny live range here. Same here. It was defined here and then used later, and we chopped it off. So in reality, what we have to do is that this is really a new program. So spilling actually will restart the whole thing. So we'll basically throw away all the stuff that we did, including the interference graph, and go back and rebuild it, because we have a program that has different liveness. It's effectively like a new program. And so this is actually the really expensive thing about graph coloring, and about all register allocators typically, is that when you insert spilling code, you have to go back and recompute all the liveness. So we're going to talk about linear scan in a second. It doesn't necessarily have to do it that way, but when we talk about the context of graph coloring, the coloring part's the easy part. Like that is a linear thing. Like this optimistic stack-based thing, that's really easy. What's hard is like going back to rebuilding the interference graph. And so you have to maybe potentially do this iteratively. The other part that I mentioned in the overview is that that's a spilling candidate. So we got stuck because we couldn't find any node in the graph, which is less than k, which means that there was at least k nodes in the graph, which means that we had to choose one of them. And so that's the heuristic about picking a spilling candidate. And so the dark art really of this kind of register allocator is going back to the program and figuring out which of those variables you actually want to spill. And so you can use heuristics like, okay, it's not used in a loop. Maybe it's something that just happens to be live across the loop, but it's not used in the loop. So that's a good candidate because it means that the spilling code, which you're going to insert, is not going to be in the loop, right? You may choose variables that have lots of interferences. They may also be, they're live for a long time, which means that if they don't get a register, you free up a register for the longest amount of time. Excuse me. So those are the kinds of things that go into a spilling heuristic. That same spilling heuristic can feed into almost any algorithm, but notice about graph coloring is that nothing in this primary data structure teaches us anything about what we should spill. It only tells us when we must spill. We get stuck somewhere in the middle. So that's graph coloring register allocation. If you want to go deeper, go read a compiler chapter on this. There's actually plenty of good material online about this, but I won't go any deeper than that because we have only so much time.